the key to doing these sort of problems is basically just being able to manipulate the main equation. So good old Pivnert, PV equals nRT. And so we'll find that pretty much all of these questions, even if they seem complicated, oh man, you're bored already, huh? No matter how complicated they are, it just boils down to just manipulating that equation to try and figure out what the question is asking. And so for pretty much all of these, we'll just look at the question, see what it is it's asking, and then try and work out how do we use PV NRT to get to the answer. Okay, so if people had a chance to look through the questions so far, then we can, try working on a couple.
Professor?
Yeah.
I have a question. I missed this lecture. Is it recorded?
Yes, it is. It'll be up. It'll be up. I still have some editing to do, but it should be up probably by Thursday, hopefully.
Okay. Thank you.
Depends how much time I have for doing it tomorrow. I need to finish the lab for Thursday, so I'll probably spend most of my time doing that, but I'm going to try and get everything up by the end of the week.
Okay, thank you.
So is there one that people would like to start with, or have a look through? I mean, we could just start with the first one.
Yeah, number one.
Okay. All right. Let me. Yes, I transferred these to PowerPoint so I have more room to draw on them. There we go. Move some stuff around. Okay. Move that over there. Okay. So, as I mentioned, pretty much what we're going to be dealing with is simply manipulating that same equation that we're going to come to know and love. PV equals N, here we go, RT. So that's sort of the key to all of these. So we look at a question and we figure out what information is it giving us, and what information is it looking for us to answer. So we have 30 liters of oxygen. Okay, so we've got a volume. So our volume is 30 liters. So we got that part. We've got 2 temperatures. So we've got temperature 1, which is 200 degrees C, and we've got temperature 2, which is 1 degree. And the pressure is constant. So P1 is equal to P2. So it's basically asking us for V2. So if V1 is 30 liters, V2 is X. We don't know what it is. So we have pretty much all the information we need to try and figure out what's going on. So what's the very first thing we need to do to start addressing the problem?
make make the PV and RT, make it equal to V.
Even before that, what do we need to do? something we need to do that even before.
How would I Google that question?
Google what? Oh. So basically what I'm asking is, when we're dealing with gases, there are certain measurements we need. There's certain units we need in order to do these problems. So pressure is going to be in atmospheres. We need to figure that out. Volume is going to be in liters. That's standard for volume. And what's the standard measure for temperature?
Kelvin.
Right, Kelvin. And we're not given Kelvin here, are we? We're given Celsius, so we need to convert them. So how do we convert Celsius over to Kelvin?
Don't we just add 270? Wait, no.
Mhm.
Add 273.15.
Yeah. So we add 273.15 to both of these. So our T2 is 274.15 Kelvin, and our T1 is 473.15 Kelvin. So that's what let me erase. So this is our new temperature. So what our new temperatures are going to be. 473. 473.15 and 274.15. Just making some space for me here. And everything else is in units we can deal with, okay? So there's a couple of approaches we can use. We can just go right ahead and try and figure out what the new volume is based on what we know about the noble gas laws. What is the relationship between, because we're changing temperature, what's the relationship between temperature and pressure? Is it direct or is it indirect? Or inverse, is it inversely related or is it directly related? As the temperature goes up, what happens to the pressure?
It goes up.
Goes up as well, right? And so if the temperature goes down, what should happen?
Goes down. So it's probably directly related.
Also directly related. And so the same thing is true of temperature and volume. Same is also true. If the temperature goes up, the volume goes up. The temperature goes down, the volume goes down. So basically what we can do here is we can just take the first volume, which is 30 liters, and since it's a direct relationship, the pressure doesn't change. You can just take, so basically V1 or V2 will equal V1 times T2 over T1. Since this is a direct relationship, if T2 is larger than T1, V2 will also go up. If T2 is smaller, if the second temperature is smaller, V2 will also be smaller. But we know it's a direct relationship. So we can just multiply the second temperature, which is 274.15, over the initial temperature, which is 473.15 K. And our temperatures will cancel. And we just basically figure, so what would be the answer here? If you get the same thing I do. What's my new volume?
$17.38.
Mm-hmm. 17.38. You're not right though. What do you need?
Liters.
Liters, right. So if we wanted to figure out how many significant digits, kind of tricky because we only have one for the second temperature. But so generally what I'll do, like on a test or something, I'll try and give you at least 3 significant digits with the temperature. As you can see, when we with 0 degrees Kelvin is 273.15. So that's 5 significant digits. But since we're only measuring 1 degree, we don't really know how accurate that number is. So let's assume that there's 3 significant digits here. There's 3 significant digits here. So actually there's only 1. There should be like a decimal place or something there. Let's just assume there's 3 significant digits. So what would our final answer be?
$17.4.
Yeah, 17.4 liters. Yeah, and so doing it this way, you don't even need to know what R is. It's not important because because what we're dealing with is a change in temperature. So we just know that something's gone from one temperature to another, and we just need to we can use the equation to figure out if they're directly related or indirectly related. So we can see that in this instance, as T goes up, P and V should both go up as well. Just by looking at the equation, we can see that if something on one side of the equation increases, something on the other side of the equation needs to increase as well. Okay, and since P doesn't change, N doesn't change, and R doesn't change, it's directly related to the temperature. And so we can just use this to figure out what the change in volume is. So is that clear to everybody how you would do that? In this instance, you don't even need to manipulate the equation. But you need to look at the equation and see what the relationships are between them. So since pressure and volume are on one side of the equation and temperature is on the other, you see they're directly related. If they're on the same side of the equation, they're inversely related. So if P goes up, B has to go down if everything stays the same on the other side. So if my number of moles stays the same and the temperature stays the same, then as P goes up, V must go down so that they stay equal to each other. Okay, but since P, V, and T are on opposite, P and V are on one side of the equation, and T is on the other, they're directly related. Hopefully that's not terribly, that too confusing an explanation. Don't all talk at once. So is that clear how to do that?
Yes.
One sad voice in the wilderness. Okay, good.
No, just sleepy.
Yeah.
It's 1 p.m., but I'm tired.
Yeah, my sleep schedule's all messed up too. I'm taking like, way too long of naps in the afternoon and I'm staying up till, 2 in the morning. It's all crazy. Watching way too much Netflix or whatever and YouTube at nighttime.
Mm-hmm.
All right, so
Me
is there
too.
another question? Should we just go to the next one, or is there a particular question? Have a look through them and see what you think. Oh yeah, and I need someone to check on the chat for me. If there's something going on in the chat that I need to answer, let me know.
Mm-hmm. There's nothing going on.
Nothing going on. Okay. Oh, now I'm gonna have to clear everything. All right, so there's the second. Is there a particular question that, this is basically the same sort of question, only changing the pressure rather than the temperature. So shall we just briefly look at this one?
Let's do it. I don't know how to do any of them.
Okay. Okay. All right, so I'll just put down our old friend.
Which number is this?
This is number
Right.
2.
2. Oh.
So let's look. So just like I said for the first question, we'll look at what information do we have and what information is being looked for. So we have a volume. So we have V1, and that is 1,400 milliliters. We have T1, and that is 25 degrees C. And we have P1, and that is 760 millimeters of mercury. So the question is, what is V2? We don't know what V2 is. So that's going to be X. And we have a P2. P2 is 380 millimeters of mercury. So in this instance, and temperature is the same.
Temperature the same.
So T1 and T2 are the same. So that's not going to change. So we don't have to worry about the temperature. So a couple things we need to change. So remember, first part of any of these questions is just write down what information we have. So we've got that information down. Second part is units. We need to make sure we're dealing with the right units. So what do we need to convert? Remember, pressure is always
Celsius to Kelvin.
Actually, we don't have to do that because it doesn't change.
Oh, pressure.
If it changed, we would have to worry about it. But since it's the same, we don't have to worry about it. Pressure, yes, we do. Pressure changes, and so we do need to worry about that. And so, how do we go from millimeters of mercury to atmospheres? Because remember, pressure is always going to be in atmospheres. For our particular value of R. So what?
Isn't the conversion 1 milligram of mercury equals to 760?
Tor.
Yeah, torr. Sorry.
Right. So yeah, 1 millimeter. It's a distance. 1 millimeter of mercury is 1 torr.
Oh.
But that doesn't help us because we need to get to atmospheres. So we need to convert. If you remember how many torr there are in an atmosphere,
760.
good, 760, right. So P1 is 1 atmosphere. That's good. That's easy to remember. But P2 is less. So how many atmospheres in P2?
0.5. So like half.
It's exactly half. And actually, if we were doing this, we could just divide P2 by P1 and we'd be fine because they're directly related. Really, the only thing that's kind of an issue is temperature, because if there's a big difference between changing the temperature in Kelvin by half and changing the amount in Celsius by half. So there's a huge difference. So here we want to figure out what is the relationship between P and V. Are they directly related or are they inversely related?
Inversely.
Yeah, because here we've got the number of moles, N stays the same, R stays the same, P stays the same. So as P goes up, V has to go down by the same amount. So the product of them will equal. So basically what we're dealing with is P1 times V1 is going to be equal to P2 times V2. Has to be, because they both have to equal the same thing. And so we can just plug the numbers in here. One other thing we can do is we can either change this to liters or we can basically leave it the way it is, because the question is what volume will it occupy? And since we're just basically the only thing that's going to change, the only thing we're dealing with changing is the pressure. We can leave it at liters, or we can leave it with milliliters, or we can convert it to liters. It doesn't really matter. But if we wanted to change it to liters, what do we change it to?
1.4
Right.
liters.
1.400 liters. So our P1 is 1, and our volume is 1.4. Now I would be putting units in here, but it's kind of hard to write the units with this particular pen here. You can see it's a little tricky. So our P2 is 0.5, and our V2 is unknown. So basically V2 is 1.4 divided by 0.5. So what's my V2?
2.800.
Yep. 2.800 what? Liters. See here, we could have used, we could have left the milliliters in, it would not have mattered, really. But if the answer was, if it asked us what the volume was in liters or what the volume was in milliliters, we need to convert it. But since this question doesn't say, it just says what volume will it occupy. So 2.800 liters or 2,800 milliliters, same answer.
Okay.
Okay?
Lemon sig going to 2
So what was the question?
for significant figures.
Significant figures, right.
It will be
Looks
2.
like we've got 2.
So like 2.8 liters.
So 2.8 would be fine. Yeah, because we got 2 here. Whoops. Go back. Oh, that was the first one. There we go. Yeah, so we've got 2 significant digits there. We've got 2 there. We've got 2 there and 2 there. So yeah. So the answer should have 2 in it. So yeah, 2.8 or 2,800 milliliters, which also has 2 significant digits in it. Yeah. All right.
Oh, it's 2 sig figs, not 4?
Not 4. No, just 2.
Okay.
So remember, trailing zeros are only significant if they're after the decimal point.
Mhm.
So the trailing zeros basically tell us how accurately we can that measurement is. And so when it's before the 0, 1400 basically tells us I'm accurate to the nearest 100. So 1400 means it's not 1300 and it's not 1500, it's 1400. So it's only these 2 digits that are significant. If on the other hand, I had 14.00, that means not only is it accurate to the nearest 100, it's accurate to here. It's accurate to the nearest 100th. So the only reason for recording these 2 zeros is because I can measure it that accurately. So here I have 1, 2, 3, 4, 5, 6 significant digits rather than just 2.
Mhm.
If, on the other hand, it was 14 decimal, that means I'm able to measure it to the nearest 1. So it's not 1401 and it's not 1399. It's 1400 exactly. So that would have 4 significant digits.
Okay.
Okay. All right. So that's the first question. Second. Third is basically the same one. Here's one.
Oh, sorry, there was a question asked.
Oh, yeah.
So depending on what they give you in a problem, you
Mhm.
use that you use to determine that what law formula to use.
Oh, always start with PV equals nRT. Just write it down. Always start with that. But then from that equation, you figure out, am I changing one thing? Am I changing 2 things? And then figure out what are the relationships. Let me go back. Actually, we'll just do it here. We'll just do this one right here. This one. So here, basically, we're not given any numbers, right? We don't have any measurements. We're just saying that something's doubled and something else is quadrupled. So like, where do you even start? So if you have a question like that, you start by writing down the equation. So I've got my PV equals nRT. So I look at this and I say, so P2, the pressure of the gas is quadrupled. So basically, P2 is 4 times P1, right? I know that. So the pressure has gone up by 4. And the temperature has doubled. So I know my T2 is twice whatever T1 is. And we're assuming that since it says absolute temperature, that means Kelvin. Because Kelvin is a measure of temperature absolutely, right? Because since it starts at 0 and goes up from there. So it's an absolute temperature. So what do we do with this information? So I go back, to the holy grail of all gas law problems. And what's my relationship between these things? So what's the relationship between pressure and volume? Because it's asking, what's volume 2 in relationship to volume 1? How does volume 2 change? So what's my relationship between pressure and volume here? If I want to work out volume 2, I need to figure out how does it change due to the pressure and how does it change due to the temperature. So how does it change due to the pressure? If the pressure goes up, what happens to the volume?
Someone said if P goes up, then and V goes down. So he's saying that volume would decrease.
Right. They're inversely related.
Mhm.
To figure out V2, I would take my P1 and divide it by P2, right? Because they're inversely related. So my relationship between volume 2 and volume 1 is the opposite of the pressure. Whatever changes to the pressure, the opposite thing happens to the volume. So this is what I'm looking for. I want to know what my relationship is between my new volume and my old one. And that is going to be, excuse me, opposite to the relationship between the new pressure and the old pressure. Now I need to multiply that by the factor of the temperature. So what happens, what's the relationship between the volume and the temperature?
Volume increases with, oh, wait, directly?
Directly, exactly, it's a direct relationship. If something increases on this side of the equation, something needs to increase on that side of the equation, so it will balance out. And so as temperature goes up, volume goes up by the same amount. So that would be,
Avogadro's law. Oh, sorry.
no, that's Charles. I think that's Charles, right? The temperature. And Boyle is I can never remember who's who. Avogadro's the easy one to remember, and the other two, I think Boyle's temperature, I think. Yeah, directly related. So the relationship between V2 and V1 will be the same as the relationship between T2 and T1 because they're directly related. So if T2 is twice as much as T1, V2 is going to be also twice as much as V1. So basically, we're done. We have all the information we need to figure this out. Basically, V2 divided by V1 is equal to 4, right? 4P1. Oh, wait a minute. No, sorry. Other way around. Now I'm confusing myself. Oh. P1 is P1. We don't know what P1 was. But we do know that P2 is 4 of them. So that's the relationship between P1 and P2. What's the relationship between T2 and T1?
T2 is twice as much as T1.
Right. So that's 2T1 over T1. So P1s cancel, T1s cancel. What's our final answer?
1/2.
1/2. So basically, if the pressure is quadrupled, what that means is that the volume will be decreased by four times. So it'll be 1/4. But the temperature doubled. So that doubles that volume. So if it goes down by a factor of 4 and then up by a factor of 2, it's 2/4. The answer is 1/2. So by what factor does the volume of the sample change? 1/2. Okay. Is that one clear? Because the next one's basically it's the same question, just slightly different. It just asks you to remember whether or not these things are directly related, and that's another key to working with the gas laws. Because notice we haven't even used R yet. We've done 3 questions and we haven't even used R yet. Basically, you only use R when you have to absolutely calculate it's pretty much the only time you need to use it, because the rest of the time you're just either changing the pressure, and so you know that that's what the relationship is. You're changing the volume, you know what the relationship is, or you're changing the temperature, you know what the relationship is. Really, the only time we need to use R is when we have an absolute amount of gas, and it's like, oh, right, okay, now I need to plug R in there somewhere. But if it's just relative changes from one condition to another, you don't even need R. You just need to know what's the effect of that change. Is it direct or is it inversely related? That's really all you need to know, and that you can figure out from good old Pivner, PV equals nRT. So you can see that this next one, is basically the same question. Although the pressure's tripled and the temperature's quadrupled, what effect that would be. So you can figure that one out. And then what about, so fixed mass of gas. Let's look for one that's, okay, here's one we're gonna need. So we've got a certain amount of gas and we need to calculate the volume. So here, we're not dealing with a change. We're dealing with absolute amounts. So now we are going to need to use R. That gives us the relationships between P, V, and T, and the actual amount of gas. So now we're going to actually have to use, we need to use R to figure this one out. So we get our color here to use. It's a pretty color. Here, use pink. So what information do we have? We have we have a mass of gas. We have a temperature, 25.0 degrees, and we have a pressure, 1 atmosphere. Oop, my internet connection's good. Everyone hear me okay?
Yeah.
Yeah.
Yeah, I had it quit this morning, so I'm a little nervous. All right, so here's our good old friend PV equals nRT. So we need to calculate V. So we don't know what V is. And we're given the pressure, we're given an amount, and we're given the temperature. And we know what R is. So basically, it's just a matter of plugging everything in and figuring out what V is. So what is N? N, remember, is what? What does N stand for?
Moles.
Moles, exactly. So we have moles of methane gas, but we're given an amount. We're given grams. We're given a mass. So we need to go from mass in grams to moles. How are we going to do that?
Oh, we use the molar mass of methane gas.
Right. So we need to. So I want moles. So we're going to put moles on top. 1 mole over. Man, this thing is not liking this pen right. So 1 mole over a certain number of grams. So that's going to be my molar mass. So what's the molar mass of methane?
16.04.
Your word for it. But yeah, it should be around 16, right? Because 12, carbon is 12 and hydrogen is 1. So yeah, it makes sense, 16. So how many moles is that?
.2 moles of.
Three significant digits, right? There's 3.
Oh, well, okay.
2.19.
2.19 moles. So I've got N in the right units. I've got P in the right units. What about T, my temperature? 5 degrees C. That's not the right units for that, right?
Converted to liters.
Converted to,
Kelvin.
Kelvin.
How do I do that?
You
Uh,
add
Multiply 275.
273.15.
Multiply? Who said multiply? 273.15. 25 plus 275. What's my new temperature?
298.15.
Yeah. 298.15 K. So I've got my T, I've got my N, I've got my P. So I'm ready to go. So V should equal N R T divided by P, right? I just divide both sides by P to get my V. So that's going to equal 2.19 moles times R. Now R is 0.0821. And if I remember a lot of units there. So it's, what are the units? Someone help me.
I don't know.
Atmosphere times
Wait, units for what? Oh, for R?
For
Atmosphere,
the
Sphere liters.
R?
atmosphere mole? No.
atmosphere times liters divided by moles times Kelvin.
That's right. Moles, Kelvin. Yep. And then I multiply that by the temperature, which is 298.15 Kelvin. And I then divide the whole thing by 1 atmosphere. So I've got atmospheres on the bottom, atmospheres on the top. I've got moles on the top, moles on the bottom. I've got Kelvin on the bottom and Kelvin on the top, and I'm left with liters, which is what I want. Oops. All right, so what's my final answer going to be?
I got 11.9.
0.9 what?
Yeah, liters. that right? 11.9 liter.
Let me see.
I got something else.
I think I'm getting something else too.
Oh,
I got 53.07 liters.
oh my god.
I got
Okay.
that 3.6.
I got 53.6.
Well, I'm rounded okay. I rounded to 6.
Yeah, so multiply, yeah, all that together. Yeah, I got 53.6 liters.
0.06, right?
No, I got 53.6. Maybe did I plug it in wrong? So it's 2.19 times 0.0821 times 298.15. No, I got 53.6.
0.08.
Oh, 290. Oh, okay. I plugged in something
Oh,
wrong.
53.6.
Okay, good. All right, yeah, so this is like one of those times, basically when you see that something hasn't changed, but you've got like, when you just are given like, 3 bits of information and you need the 4th, that's when you're going to need R. Generally, you don't even need it if like, the pressure changes or the volume changes or the temperature changes, but the number of moles doesn't, then you usually don't need R. R you get into when the number of moles is important. Usually that's when R comes in, unless it's a change. When you have to calculate the absolute number, then basically then we need to use R, and then we need to have all the units there. So is there another one? Shall we do like 2 more? Is there a question in the chat?
What does R stand for again?
R is the constant that binds all of this stuff together. And the way that R was calculated is that 1 mole of gas takes up 22.4 liters of volume, right? That's the standard volume for a noble gas, or not a noble gas, an ideal gas at 1 atmosphere and 0 degrees C, which is 273.15 Kelvin. So how we come to R is R brings all these things together, brings together the volume, the pressure, the temperature, and the number of, so the volume, the number of moles, the temperature, and the pressure. So basically what it is just 22.4 liters divided by 273.15 Kelvin. That's basically what it is. It's that relationship between the volume and the temperature for 1 mole at 1 atmosphere. So N is 1 and P is 1, and it's just a relationship between the volume and the temperature. Okay? That's what R is. That's where that number comes from. So you won't have to memorize it. I'll always give you those numbers along with the units. But it just, you were asking me like where it comes from. That's where it comes from.
Mm-hmm.
Okay, so is there another one we should do? How about, so density we sort of went over. So here we're going to need to use R as well. So shall we do this one together?
Yeah, I'm down for it.
I'm up for it. All right. So here's our friend. Always going to write that down. So density in grams per liter. So of chlorine gas. What's the formula for chlorine gas?
CO2.
What is it?
CO2.
Cl2, right. So we're first going to, so we need grams. So basically what we're going to do here is just assume we've got a mole, right? So we've got, if we just have 1 mole at standard temperature and pressure, how many liters is that? We just did it a second ago.
22.4.
22.4, right. 22.4 liters. I think it's 22.40, like that.
414.
414, is it? Okay. Oh, hell, might as well use all of it then. So 22.414 liters. So that is our volume. So we just need to figure out how many grams that is. We're basically done. We don't even need PV NRT for this one. So that's our volume. And we have 1 mole. So how many grams do we have? So 1 mole times grams per mole will tell us how many grams we have. How many grams of Cl2 are in a mole?
35.45.
9.
35 point, what is it?
45 in 1 mole.
45.
Because that's, yeah, 35.45, right? Because that's the molar mass.
So
What-
CO2
That's the molar mass of chlorine. What's the molar mass of
Oh,
so times 2, which is like 7.
got it.
times 2?
70.9.
All right, 70.9. Right, so it's 70.9 grams. So remember, and this happens a lot. Like, I think I mentioned it in class this morning. Pretty much all gases, except for the noble gases, are 2 atoms: H2, Cl2, N2, O2. Pretty much all of them. And so you always have to take the molar mass and multiply it by 2 because there's 2 atoms in the molecule. So if we have 70.9 grams and we are in a volume of 22.414 liters, what's my density?
.16.
Not an answer yet.
Grams per liter.
There you go. So if this question was not an STP, what probably let's say instead of standard temperature and pressure. Anyway, what is the standard pressure? And tell me what the standard pressure is. We're dealing with gases.
Uh,
1 atmosphere.
1 atmosphere, right? So that's the standard pressure. And what's the standard temperature when we're dealing with gases?
Kelvin?
Or Celsius, either one.
Mhm.
Wait, the temperature?
Standard temperature.
Yeah, standard temperature for gases. This is standard pressure. What's our standard temperature?
And the
273.
273, right, 273.15 Kelvin. So that's our standard temperature and pressure. So if the question was a different temperature or a different pressure, probably the way to approach this is to figure out what the density would be at standard temperature and pressure, and then change it accordingly. So if the pressure changed, we do, what's the relationship between volume and pressure?
Inversely.
Inversely proportional, right? Yeah, exactly. And so since this is based on our volume, if the pressure went up, does the volume go down or up?
Sorry, can you repeat that?
If the pressure goes up, what happens to the volume?
It decreases?
It decreases. So they're inversely proportional. But what happens to the density? If the pressure goes up, what happens to the density? Since if the pressure goes up, the volume goes down, what happens to the density?
Does it go down?
The volume goes down. What happens when the volume goes down to the density? Is volume in the numerator or the denominator?
Denominator?
It's in the denominator, right. So if this volume goes down, what happens to the density? If the denominator gets smaller, what happens to the density?
It gets, somebody says it goes up.
Yeah, it gets larger. Yeah, if the denominator gets, if you're dividing something, if you divide by something smaller, your overall answer gets bigger. And so here, we would take P2 over P1. Because if the pressure went up, the density would go up too. Okay? It may seem a little like, huh? I thought it was inversely proportional. It is. But because the volume is in the denominator, that means the density is directly proportional to the pressure. Because the pressure goes up, volume gets decreased, and since the volume gets decreased, it's got to be denser, right? Because we have same number of molecules now in a smaller volume, so the density's got to go up. And so if the temperature changed, what happens? So if the temperature goes up, what happens to the volume? Up or down?
So if the temperature goes down,
Okay, that's good. If the temperature, let's say, if the temperature goes down, okay. What happens if the temperature goes down? What happens to the volume?
It goes down.
It goes down as well, right? Because the molecules start moving as quickly, and so they don't hit the sides of the container as much. The volume is going to decrease at the same pressure. So the temperature goes down, the volume goes down. If I put my balloon in the freezer, it shrinks, right? So if the volume goes down with the temperature going down, what happens to the density? So the volume goes down, what happens to the density? Same thing that happened here. Pressure went up, volume went down, density went up. Here we've got the temperature goes down, volume goes down. What happens to the density?
It goes up.
It goes up, yeah. Whenever the volume goes down, the density goes up. Doesn't matter how. The volume could either go down because I've increased the pressure, so I'm squeezing it more, or the volume goes down because I've thrown my balloon in the freezer and the volume goes down. Either way, the volume's decreased. And when the volume's decreased, the density goes up. So in this instance, pressure, and the first time we've got pressure and density are directly related. And here we've got temperature and density are inversely related. So I would go T1 over T2. So basically what you just figure out whatever the density is at STP, this is my density at STP. And then whatever the pressure change is, here's my change in pressure, here's my change in temperature. Okay? Does that just confuse the hell out of everybody? Yeah, just use good old PivNerd and that will tell you what happens. Because here we've got density. Density is the mass over the volume. So density and volume are inversely proportional, right? You're dividing them. So if my volume goes up, my density goes down. So just use this to tell you if my volume changes, if my temperature changes, what happens to my volume? If my pressure changes, what happens to my volume? And since density is inversely related to the volume, it'll have the, whatever change happens to volume, it'll have the opposite effect on the density. Okay, that got way more complicated than I wanted it to. I just showed you, like, if you had a change in temperature or pressure, what you would do. We'll talk more about this on Thursday. All right, so we do one more before we head out. I'll let you guys pick the last one.
Number 12.
Number 12, okay.
Only if the others agree.
I'm fine with that.
Fine.
Okay.
I think everyone else is just wants to have a nap. I can't say I blame them.
I'm hungry.
Yeah, man. I just like wolfed something down between class and this. You guys probably do the same thing. So 12. It's
Only had a singular cracker.
ooh, and a singular one at that. That's not.
Go eat something. It's not like anyone can see.
Which one's 12?
Yeah, but I want to do my recitation.
Next, I go to the end. I know that one's 15. Oops,
A
15,
pressure that will support a
14,
column.
15, 14.
This one.
Okay,
Okay. Is it this one?
all right.
Yeah.
Doesn't even involve gases. The dogs are getting ready to go. They haven't been out since this morning. Okay. All right, so pressure that will support a column of mercury to a height of 256 millimeters. So the pressure is 256 millimeters. So it will support a column of water to what height? So basically it's saying if that pressure will push down on a column of mercury and raise it up to 256 millimeters, how much would that same pressure push up the water? So what is even though we're not dealing with gases, we can look at the relationship between pressure and volume. And that's basically what we're dealing with here, right? Because density is a function of volume and function of the mass. So what is the relationship between pressure and volume?
Inversely.
Inverse.
Right, they're inversely related. So P is basically related to 1 over the volume. And we just talked about before, when we were dealing with density, that density was related to the mass over the volume. So the pressure, if it is directly related to the volume, what's its relationship to the density?
I wasn't listening, sorry.
So our relationship between pressure and volume is 1 over, pressure is related to 1 over the volume. As pressure goes up, volume goes down.
Mm-hmm.
Density is related to the 1 over the volume as well. So my relationship between, what's my relationship between pressure and density?
They should
Is
be
it direct or indirect?
direct.
Pressure and density. Direct?
Direct, yeah. So we have a look over here, and our density of mercury is this much. The density of water is this much. So basically, the pressure on both has to be the same. And so if that pressure, if that same pressure can raise a column of mercury 256 millimeters, how high could it push the density of water? Now, since it's a 13.6 to 1 ratio, so would that pressure push the column of water higher, or would it push it lower? So just think of it this way. So mercury is really, really heavy, right? So that pressure moves that amount, basically moves this amount of mercury. So it's 13.6 grams per centimeter, cubic centimeter. And it moves it a total of 2.56 centimeters. So it can move this much by this much height. So if it weighs, if that same, if it's 13.6 times less dense, will it push it 13.6 times higher or 13.6 times lower, do you think? I mean, if mercury was half as dense, would it be pushed twice as high or half as high? Think of what effect pressure has on the, remember, pressure is force over an area. So we're dealing with the same area, but the force on that mercury is pushing back with 13.6 times more force than water, right? Because it's 13.6 times heavier. So that force that mercury is pushing down against the atmospheric pressure is 13.6 times more than water. So in order to balance out, does that water need to be, do we need more water or less water to balance that out?
More water?
A lot more, right? because this force is the same. And that force is the same. It's the same atmospheric pressure. And so since Mercury pushes down 13.6 times more than water does, you need a whole lot more water to equal that amount of force. And so if that pressure can push Mercury up 256 millimeters, it would push the water 13.6 times more. That would have to have that much more water to equal that amount of mercury. And so it would just be 256 times 13.6. So that same column of water would be 3,480 millimeters. It's basically, it's the same mass. That force is exerting the same mass over that same area. And so you need to have a lot more water to equal the same amount of mercury. a lot of quiet there. It's sort of just they just have to think about that one a little bit.
We can multiply millimeters by 13.6 grams over centimeters cubed.
Yeah, it's just because the centimeters cubed cancel out, and it's just a matter. It's just the masses. It's just a ratio of the masses. Okay, I'll let you like scratch your heads on that one. You can look that up as well. See if you get the same answer. All right, so I think we did about half the questions, if not a little bit more. So any other questions before we sign off?
I have a lot more, but I don't want to
Okay.
waste your time. So
Oh, no. I'll hang out for a little while. What else do you?
I think number 11, it says something about decomposing. Was it that one?
Okay.
Oh, what massive KClO3 must be decomposed to produce something?
Mm-hmm.
No.
That is a stoichiometry problem in of a gas laws problem. So first thing we need to do with this one is to write out a balanced equation. So I've got potassium perchlorate. It's a solid. And when it decomposes, what does that mean? When something decomposes.
I forgot.
Basically, it breaks down, right? It breaks down chemically. And so we know that it has two products because it tells us. One product is oxygen gas, and the other product is solid KCl. So we know it makes KCl and oxygen gas, which is what?
O2.
O2, right. So is that a balanced equation?
No.
Nope. So somebody balance it for me. So decomposed means you put some heat on it, basically, and that's what this triangle means over the arrow. It means you add heat. Decomposes into this solid and this gas. Somebody needs to balance that equation for me.
You multiply KClO3 by 2,
Okay.
and then you multiply KCl by 2, and then O2 by 3.
Yeah, that looks like that works. Okay, so that is our balanced equation. Now it's from here, it's basically it's trying to figure out stoichiometry. what's the relationship between products and reactants? Because it's asking how much reactant do we need? So it's asking how much of this do we start with if we release 126 liters of O2 at this temperature and this pressure. So basically that's a straight up Pivnert question. So we just plug in our atmospheres. So 0.880 atmospheres times volume, 126 liters, equals N, which is moles. That's what we need to figure out, right? We don't know what moles are. Times R, which is 0.0821 atmosphere liters over K. Did I screw that up again? K moles?
And that's the
Or is it mole? I think I
Moles,
screwed.
Moles and then
moles
K.
having-
I'm always getting that one wrong. Anyway, so what are my units again? Because I want to,
Temperature.
it is atmosphere. So it is atmospheres, right? Atmosphere liters. There we go.
And moles.
Over moles
Okay.
K. And times our temperature, which is 133 degrees, which is how many Kelvin?
406.
133 plus 273.15. 406.15. So what is my N? What's the number of moles?
$3.325
Three.
moles of.
Hmm.
Oh,
I got something
I'm not
different.
right.
Let me, I did it the wrong way. You're right. 88 times 126. Yeah, 3.325, right? Is that what everyone?
yeah.
Right. And you could remember, you can hang on to as many significant digits as you want until the end. So that's how many moles of oxygen are created when you heated up the potassium perchlorate and it decomposed into the gas and the solid. So the other product we don't really care about because it's just we don't need to know that in order to figure out how much of the starting material because we have a balanced equation. So if I have 3.325 moles of O2, how many moles of potassium perchlorate do I have? This is my moles of O2 right here. How many moles of perchlorate? How do I use the balanced equation to answer that question?
So use the ratio given from the balance equation.
Exactly. What is my ratio?
Is it 3/2 or is it the other way?
It depends. It depends. What's the relationship of perchlorate to oxygen? Because that's what we want, right? Because we have moles of oxygen. We want moles of perchlorate. So really what I want is what's the ratio of perchlorate to oxygen? Because when I multiply it, my oxygens will go away and I'll be left with perchlorate. So what's my ratio here?
2
2
over
to 3.
3.
2 over 3, that's right. 2 divided by 3. So basically I'll multiply 2 over 3 times this many number of moles of oxygen. And that gives me the number of moles of my starting material, which is how many?
Oh God, I don't know.
I mean, all you gotta do is multiply 2 over 3 times number of moles of oxygen.
I've gone 2.217.
Mm-hmm. Yeah, 2.217, which makes sense, right? Because if it's if for every 2 moles of perchlorate, you get 3 moles of oxygen. If you have a little more than 3 moles of oxygen, you got to have just a little more than 2 moles of perchlorate, right? It's a 2 to 3 ratio. So that's how many moles of this you have. Now,
And we're looking for mass.
all you need to do is convert moles to grams, and you're done. So it looks like it's a terrifying problem, but yeah, it's just a stoichiometry problem disguised as a gas problem. And you guys are like stoichiometry experts, right? I mean, you're old hands at it by now. So yeah, so this is an exam question. So I'm just letting you know that now. Yeah, this is an exam question because it makes you think, right? It makes you think like, oh my God, what do I do with this? Because there's a lot going on. You got to balance an equation. You've got to do the stoichiometry of that equation. You got to work out like how many moles of oxygen there is. So there's a lot going on. So this is why would be on a test. Just saying. Okay, you should be able to crush all the rest of them now. Anything else before we go? There's something else popped up in the chat. Was there something other than saying I'm a bad person? Is there anything else?
Oh, no. I answered it.
Okay. You're right. He is a bad person. All right. So yeah. So hopefully I'll be able to have enough time to post all this stuff before the end of the week, and then I'll have an announcement class on Thursday about the test, and then yeah, should have the lab ready to go on Thursday as well. A lot to do this week. Anyway, so that's it. Stay well, everyone, and I will talk to you soon. And remember, if you have any other questions, yeah, I'm amenable to meeting online or any time you guys need it. Okay. All right. So I'll see you soon. Take care of yourselves. All right.
Thank you.
All right.
Bye.
Bye bye.
Bye.